Good morning, folks. So we are moving into a new chapter, chapter 13, called Sequences and Series. Now, before we get too far into this, we are skipping momentarily chapters 11 and 12. Normally, we would cover those in order, but because of the slower pace of remote learning, we are going to prioritize what chapters remain that we have to cover in order of what's going to most benefit you guys for calculus next year. So sequences and series is a bit more relevant than what is covered in chapters 11 and 12. So that's why we're skipping over those. If time allows, we will certainly go back to those too. So sequences and series is nothing new to you coming from Algebra 2 last year, and it's also not really a very difficult section altogether. So it's a nice little pause in the rigor of the year. So 13.1 just covers a very simple introduction to what sequences are and introduces two specific cases of them. So an arithmetic sequence and a geometric sequence. So this is just reintroducing some vocab that you should already be pretty familiar with from Algebra 2. So an arithmetic sequence is a sequence of numbers that is defined by adding a constant term to get from one to the next. So a sequence in general is just simply a series or a list of items in a rule. Arithmetic sequence is one where the rule is that I'm always adding the same number from one term to the next. We call that number that we're adding the constant difference, and it's often associated with D, the letter D for difference. Okay. So in the sequence we see here that my mouse is wavering above, we have subscripts for each term in the sequence. So like the fourth term in the sequence in this list is 15. So we call it A sub 4, and that is equal to 15. If I wanted the 117th term, it would be A subscript 117, and that would be associated with whatever the value of that term is. So next quick example, 7, comma 1, comma -5, comma -11, so on and so forth. Still an arithmetic sequence because even though we're only seeing 5 terms, the pattern is evident that every single term you're subtracting by 6. So the common difference is -6. And again, our first term, A1, is 7. A1 is going to be very important for a lot of our formulas, you might recall. The rest of the terms might be asked for, but the first term is really what's going to set the tone for a lot of our future terms. You know me by now. I'm not going to stick to just whole numbers, just nice numbers. So we can certainly see fractions, expect that. So with the sequence down at the bottom here, it's still arithmetic. Our first term is clearly 1/3, but the common difference, you might want to set a common denominator to make it a little bit more evident. We're adding 1/6 every single time. Okay, so here we see kind of a little bit of repetition in where, and this is that first rule we saw, excuse me, the first sequence we saw, where you're constructing every term in our sequence. A1 is listed, A2, A3, A4, A5, A6. You're all adding a certain number of those common differences to your first term. So A2, you start with your first term and you add your difference one time. In order to get to A3, you start with your first term and you add your difference 2 times. And A4, you'd be adding your common difference 3 times, and so on and so forth. Well, this kind of generates a pattern for a more general rule for this term where we start with our first term 3 and we're adding our common difference 4 n minus 1 times. And n would be whatever term value we want to achieve. And that leads us to our first formula for the chapter. Our general term, which is simply the title of the arbitrary term in an arithmetic sequence, or really any sequence, but the general term for specifically arithmetic sequences is given by A sub n, that's the general term, is equal to A1, your first term, plus n minus 1 times d, d being your common difference, whatever that pattern that follows from our rule for arithmetic sequences. N is whatever term number in our sequence we're seeking to find. So if I wanted to find the 117th term, n would be 117. So, excuse me, the pattern we're seeing in front of us with this definition, we have our first term identified as 7 from the sequence listed on the top. And you can very quickly see the pattern is you're subtracting 6 every single time. So our common difference is 6. N is going to be a variable. N is you're leaving that as a place value to plug in to then generate an nth term. Now, the general term formula on the top here is pretty easy to work with once you understand it. So there's that last example with the fractions again. We already identified our first term A1 and our common difference D, which is 1/6. So this formula right here is our general term. And again, our general term is not going to be a value, it's going to be an expression. And if we want a specific term, or that's when we plug in that specific place value for n. So for instance, if I want my 61st term, I'm going to plug that into our general term formula as n, and I start to just simplify. So if I'm plugging in n equals 61, I evaluate and I end up getting 31/3 as the 61st term of this specific arithmetic sequence. I'm going to skip forward for a couple examples here because it's pretty repetitive and I trust you guys. This is pretty straightforward. Again, you've already worked with this. I do want to get to a geometric sequence now. Again, it still follows a rule. It's a list of numbers, potentially a finite list or an infinite list, but geometric sequences specifically are such that one term is always multiplied by a common ratio to get to the next term. So the common ratio is going to be labeled R, and you're always going to multiply by the same R value from one term to the next to the next. So again, we quickly see that our first term plays a pivotal role in what's constructing the next terms. So in the sequence we see here, A1 is 3, and our common ratio is 2. Very clearly, we're doubling every single term. And that's what's generating the sequence. So what you're starting to see in terms of generating a formula is if I have this 5, 10, 20, 40, 80 geometric sequence, A1 is 5, A2 is your first term times your ratio, which in this case it's 2. Your third term, I would need to multiply by your ratio 2 times before getting your A3. Your fourth term, I would need to multiply by my common ratio 3 times before generating that, and so on and so forth. So what we see is very quickly, I'm going to skip a little bit of the specifics here. Our general term for a geometric sequence is your common ratio ends up being raised to an exponent n minus 1, and that is what's being multiplied by the first term, A1. So for instance, if I want the 11th term of a sequence, I'm going to take my common ratio and raise it to the 10th power multiplied by my first term. So the sequence we see in front of us, we have a very clear, obvious A1 is 2, and you can very quickly just divide two consecutive terms. You have your common ratio is -3. So I'm multiplying by -3 every single time. So R is -3, A1 is 2, and whatever term I deem that I need to find is very quickly found by just using our general term formula. So if I want the 15th term, I'm going to plug in 15 as N, I'm going to plug in -3 as R, I'm going to plug in 2 as A1, and I can quickly compute this to be this rather large 9.5 million some number. So it's not all that difficult to work with these two formulas. Um, Finding a common difference is as simple as subtraction. Finding a common ratio is as simple as dividing consecutive terms. So again, I'm going to move a little bit fast through this. I know you have the pause button if you want to pause this. This is a lot of repeated examples. So moving on, excuse me, to one just key component that I want to end on. If your first term is compared the same for an arithmetic and a geometric sequence, and your common ratio is the same as your common difference between the two, it should be no surprise that the geometric sequence is going to increase. It's going to grow much, much faster. It's an exponential formula after all versus a linear formula. We have a constant rate of change versus a multiplicative rate of change. Okay, so this is a quick, brief refresher slash introduction of these two sequences. Take a look at the homework, work through it. We will build on this concept tomorrow. Good luck.